Here we will derive the lens maker's formula. It is the formula relating the focal length of lens, refractive index of material of the lens, and the radii of curvature of its two surfaces. And this one is the formula. It is so named because the lens manufacturers use this formula to make the lenses of particular focal length or power from the glass of a given refractive index. Now see, this is the required ray diagram for the derivation of the lens maker's formula. Here we have taken a convex lens, but instead of convex lens we can also make the derivation by using a concave lens. So now let us understand this diagram properly before starting our derivation. So this one is the required ray diagram for the derivation of lens maker's formula. So see, here we have taken a convex lens having the spherical surfaces S1 and S2. Here the spherical surface S1 has the radius R1 and the spherical surface S2 has the radius of curvature R2. Here C is the optical center of this lens, and C1 and C2 are the center of curvatures of the spherical surfaces S1 and S2 respectively. Here we have taken a point object which is situated upon the principal axis of the lens. From this point object, OM is the incident ray upon the surface S1. Now at the point M, as we know, we have to draw a normal. So here C1M is the normal to the spherical surface S1 at the point M. Again, we know that the radius of curvature or radius of a spherical surface is the normal to the surface at that point. So this CM, which is the radius of curvature, is also the normal to the surface as at the point M. Now here let the refractive index of this lens be mu2 and the refractive index of this outer medium be mu1, so that the refractive index of the lens is more than that of the refractive index of this outer medium. Basically this outer medium is taken as air, but here we have taken any medium having refractive index mu1. But if it is air, then instead of mu1 we will write 1 because the refractive index of air medium is 1. Now see, at the point M, refraction takes place as the light is travelling from a optically rarer medium to a optically denser medium. So the ray will bend towards the normal. So here CM is the normal and this one is the direction of the incident ray. Now due to refraction at the point M, this ray will bend towards the normal. So this is the bending of the ray. This one is the bending of the ray. And Mn is the refracted ray for the refraction at the point M. Now if the whole space at the right side of this surface S1 be filled with this medium having refractive index mu2, then this refracted ray would go straight and meet the principal axis at the point I1. But as it is a lens, so refraction again takes place at the point N, because now this ray Mn again move from this optically denser medium to this optically rarer medium, or this Mn ray will move from the lens to this outer medium having refractive index mu1. So here at the point N, refraction takes place as the ray is travelling from a optically denser medium to rarer medium, so it will bend away from the normal. So at the point N, C to N is the normal to the surface S2, which is also the radius of curvature of this surface S2. Now see, this would be the direction of this ray Mn, but due to refraction at the point N, it will bend towards away from the normal. So as it is the normal, so it will bend away from the normal. So this one is the bending of ray. So this Ni is the refracted ray. So finally the ray meet the principal axis at the point I. See, here O is the object, I1 is the image for the refraction at the point M. It is a virtual point because ray again bend at this point N, so it has no real existence. But yes, if we draw this ray Mn in the forward direction, then it would meet the principal axis at the point I1. So for the refraction at the surface S1, O is the object and I1 is the image, but for the refraction at the surface S2, I1 is the virtual object and I is the image. So for this lens, O is the object and I is the image, and refraction takes place at two surfaces S1 and S2 at two different points M and N respectively. Now let us start the derivation. For this derivation, we need the formula, this formula which we have already derived. The formula of the refraction at a spherical surface. See, here we have taken a concave spherical surface, and this is the required formula for the refraction at a spherical surface. Also we have we made the derivation of the refraction at a convex spherical surface. There also we got the same formula, that is mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. We will apply this formula for the refraction at two spherical surfaces of the lens. Now let us start the derivation. So for the refraction, at surface S1, that is, here ray is travelling from moving from optically rarer to denser medium. So the formula for the refraction at a spherical surface is mu2 by V minus mu1 divided by U is equal to mu2 minus mu1 divided by R. Now let us put all the values here for the refraction at this surface S1. So for the refraction at surface S1, see here the object distance is O P1 and the image distance is P1 I1, and here the radius of curvature for the first surface is P1 C1. Now let us put all these values here. So mu2 divided by, here V is P1 I1 minus mu1 divided by object distance is O P1, that is equal to mu2 minus mu1. Here OP1 is negative, so we will write it as negative minus OP1 because it is against the incident ray, or it is at the left side of the point P1. Mu2 minus mu1 divided by R. Here R is the radius of curvature of this first surface S1, which is P1 C1. P1 C1. Now let us write it as mu2 divided by P1 I1 plus mu1 divided by O P1 is equal to mu2 minus mu1 divided by P1 C1. Now let us make an assumption that P1 and C are very close to each other. Obviously, in comparison to this object distance and image distance, this distance P1C is very less. So the distance P1I1 is comparable to or nearly equal to that CI1, and the distance OP1 is nearly equal to OC. Now let us put these values in the above equation. This implies mu2 divided by CI1 plus mu1 divided by OC is equal to mu2 minus mu1 divided by P1 C1. So write this as equation number 1. Now for the refraction at the second surface, for the refraction at surface S2, here ray is moving from denser to rarer medium. Ray is moving from denser to rarer medium. See, again we will apply the same formula, that is mu2 divided by V minus mu1 divided by U is equal to mu2 minus mu1 divided by R. Now let us put all the values for the refraction at the second surface. Here for the refraction at this surface S2, the first medium is having the refractive index mu2 and the second medium is having the refractive index mu1, or light is travelling from the medium having refractive index mu2 to the medium having refractive index mu1. So here the second medium is having refractive index mu1, so let us write it as mu1 divided by, here V is the image distance, here image is P2I. For the second surface, image distance is P2I, so let us write it as P2I minus, for this refraction at the second surface S2, first medium is having the refractive index mu2, or the incident ray is in the medium having refractive index mu2. So we will write it as mu2 divided by, here the object distance is P2 I1. P2 I1, because I1 is a virtual object here. And both P2I and P2I1 are positive because both are at the right side of the point P2. This is equal to, now here the second medium is having the refractive index mu1 and the first medium is having the refractive index mu2. So mu1 minus mu2 divided by, here the radius of curvature is P2 C2, but it is at the left side or against the incident ray, so we will write it as minus P2 C2. This implies, now see, again we apply that assumption that C and P2 are very close to each other, or in comparison to this image distance and object distance, C P2 distance is very negligible or very less. So P2I is comparable to CI and P2I1 is comparable or nearly equal to CI1. Let us put these values in the above equation. This implies mu1 divided by Ci minus mu2 divided by Ci1 is equal to mu1 minus mu2 divided by minus P2 C2. Now here it is minus, so we can write this equation as a, this implies mu1 divided by Ci minus mu2 divided by Ci1. So this can be written as, now let us interchange mu2 and mu1, and this the sign will change as it here is a minus P2 C2. So mu2 minus mu1 divided by P2 C2. Now give this as a equation number 2. Now let us add this equation 1 and 2. So adding equation, actually we are adding equation 1 and 2 because we want to cancel this term Ci1, because I1 is a virtual point because it has no real existence. So we want to cancel out this term. That's why we are adding the equation 1 and 2 here. See, so mu2 C, sorry, adding equation, now adding equation equations 1 and 2, we will get, see, mu2 divided by Ci1 plus mu1 divided by OC plus, second equation is mu1 divided by Ci minus mu2 divided by Ci1. This is equal to mu2 minus mu1 divided by P1 C1 plus mu2 minus mu1 divided by P2 C2. So this implies mu2 divided by ci1 plus mu1 divided by OC plus mu1 divided by Ci minus mu2 divided by Ci1. This is equal to, here mu2 minus mu1 is common to both the terms, so mu2 minus mu1 1 divided by P1 C1 plus 1 divided by P2 C2. See, this implies here these two terms will be cancelled out. So mu1 divided by OC plus mu1 divided by Ci is equal to mu2 minus mu1 divided by 1 by P1 C1 plus 1 divided by P2 C2. So this equation here mu1 is common to both the terms, so we can write this. This implies mu1 1 divided by OC plus 1 divided by Ci is equal to mu2 minus mu1 divided by mu2 minus mu1 into one by P1 C1 1 by P1 C1 plus 1 by P2 C2. Okay. So this implies, now let us take this mu1 to right hand side. So 1 by OC plus 1 divided by Ci is equal to mu2 minus mu1 divided by mu1 into 1 by P1 C1 plus 1 divided by P2 C2. So this implies 1 by OC plus 1 divided by Ci is equal to mu2 minus divided by mu1 minus 1 into 1 by P1 C1 plus 1 by P2 C2. Now let us put the values for this lens. Now for this lens, O is the object and I is the image. Although refraction takes place at the two different surfaces, but here O is the object and I is the final image. So here OC is the object distance, that is equal to minus U, and Ci is the image distance, that is equal to V, and here P1 C1 is the radius of curvature of the first surface and P2 C2 is the radius of curvature of the second surface. Now let us put all these values for the lens. This implies 1 divided by OC is the object distance, that is minus U, plus 1 divided by Ci, Ci is the image distance, that is V, is equal to, this is mu2 divided by mu1, we can write this as mu2 1 minus 1 into here 1 by P1 C1. P1 C1 is equal to R1, that is the radius of curvature of the first surface, minus, as P2 C2 is minus R2. P2 C2 is minus R2, it is at the left side of the lens, So 1 divided by minus R2, so it will be equal to minus 1 by R2. So this implies 1 by V minus 1 by U is equal to mu 2 1 minus 1 into 1 by R1 minus 1 by R2. So, but we know that 1 by V minus 1 by U is the 1 by V minus 1 by U is equal to 1 by F, that is the Lenz's formula. But from Lenz's formula, that is 1 by F is equal to 1 by V minus 1 by U. Let us put 1 by F instead of 1 by V and 1 minus 1 by U. This implies 1 by F is equal to mu 2, that is the refractive index of second medium with respect to first, or into 1 by R1 minus 1 by R2. So this is the required lens maker's formula. Now see, if the first medium is air, that is if first medium is air, that is mu1 is equal to 1 and mu2 is equal to mu, say that the refractive index of the material of the lens be mu, say, then the above equation become, this implies 1 by F is equal to, this is mu 2 1, that is mu 2, instead of mu 2 we will write mu, and this mu 1 is 1, so mu minus 1 into 1 by R1 minus 1 by R2. If mu is 1 for air medium, for air medium, this is for air medium. So this is the final formula.